Hello, and welcome to our next set of college algebra notes. We're on Unit 3, Outcome 5. We're about halfway through Unit 3, so we're getting close to the end. In this section, we're going to work on solving equations that involve either exponential expressions or logarithmic expressions. What this really means for us is that we're going to solve equations where x is either in the power or x is inside a log. So there's going to be two different types of equations we solve. And then each type of equation will actually have a couple different techniques. We'll actually cover like 4 different main techniques on how to solve them. The first technique isn't used very often, but if it can be used, it's a lot easier maybe than other methods. And this is saying if we have x in the power, if we're solving for something where we have powers, one of the tricks is noting that if the bases match and things are equal, then the powers have to match. So this is due to the one-to-one property of exponential functions. But the one-to-one property says that if something with bases match, then the powers have to match. So if the things with bases match, then the powers have to match. So we can take an equation that has powers like this and note that since the bases match, we can just set the powers equal. We can say for this equation to be true, for this to work, the powers have to be equal. So we'll drop the 4's and we'll just say, because these are the same 4 base, these powers, 6 and 2x, have to be the same number. You can't take 4 to the 6th and 4 to the 5th and get the same answer. For them both to be equal, they both have to be 4 to the 6th, which means that this 2x has to be equal to 6. So 6 has to be equal to 2x. And that's the big trick. If the bases match, you can just rewrite it as just the powers equal. And then you solve this and you'll figure out what x needs to be. So we'll just divide both sides by 2. Divide by 2 here, get rid of that multiplication by dividing, and we see that x has to be, well, 6 divided by 2 is 3. And you can check that, right? If you put 3 in here, you get 2 times 3 is 6, and 4 to the 6 is equal to 4 to the 6. They give you the same answer. I don't know what the number is. I know that they'll be the same because the powers are the same. So that's our answer. So this is the big trick. Now, it's not always quite that simple, because a lot of times the bases don't look like they match when they start. So you get a problem like this one, where 3 and 81 are not the same number. The bases don't match. But in this problem, you could take 81 and you can replace it with 3 to a power. So we're going to replace the 81 with 3 to some power. So we just got to figure out what power it is. Well, 3 times 3 is 9, times 3 is 27, times 3 is 81. So 3 to the 4th is 81. So we'll replace that 81 with a 3 base thing. That way the bases will end up matching. You're always going to take the bigger number. It's always the big number that you're going to replace with that same base but to a power. So I'm taking this 81 and replacing it with 3 to the power. Now this only works if you can get that power. So if I got a number like 82 here, well 3 doesn't go into 82 and I wouldn't be able to do this. But since 81 I can do 3 to a power and get 81, I can replace that. So I'm going to rewrite this as 3 to the x equals 3 to the 4th. I'm replacing 81 with the same amount, right? 3 to the 4th is equal to 81. They're the same amount, but I'm replacing it so that now we have two things with powers where the bases actually match. If the bases match, then we can set the powers equal. So the answer for this one is 4. Now it's a pretty simple one because over here we just have x. But this works anytime you have numbers where you can get the same bases, no matter how complicated the powers get. So this is just the idea. If you can get the bases to match by replacing the big number with that base to a power, you can make it work. So we'll try another one. Okay, go on the next page. This one's a little more complicated here. But notice that all 3 of these numbers, 25, 5, and 125, can all be replaced with 5 to a power. In fact, we don't have to do 5 because it already is a number. So we can replace 25 with 5 squared, because 25 is 5 times 5. And we can replace 125 with 5 cubed, because 125 is 5 times 5 is 25 times 5 is 125. So we're going to replace both of those. Now, these ones, the difference here with the 25 to the x, notice that it already has a power. So when we do this, we got to remember we're just replacing the 25, the x power is still on it. So I'm going to replace 25 with 5 squared. So I get 5 squared here, but the 25 does have that power x, so we're still going to have that power x. Still times this 5, which is to the x plus 2 power, and equal to 125, and that one we can just replace with 5 to the 3rd, and there's not much to that because that is replaced. So we're good to go. Okay, so now we've replaced that. So now we have all these matching bases, except over here we have this parentheses because this whole 5 squared is being raised to the x power. So to get rid of this parentheses, what we're going to do is we're actually going to use a power rule. Remember the power rule for powers. It says that if you have a power to a power, you multiply the powers. So I'm going to take 2 times x. So this becomes 5 to the 2x power. So that's a, oh, not x down there, x up here. X plus 2 equals 5 to the third. So that's the power rule. The power rule says that when you have 2 powers where you have a power to another power, you multiply the powers. Next thing we're going to do is here we note that we have multiplication with these two 5s and they both have powers. Remember in this case you do the product rule because you're doing multiplication and it turns into adding the powers. With the product rule you add the powers. So I'm going to get 5, same base, it's going to stay the same, but now I'm going to take these powers, the 2x, and I'm going to add the x plus 2. All of that was just to get it so now we have the matching bases. When I have more than one base, it doesn't work. If I have something like with the parentheses, you can't do it yet. Here I had 5 squared to the x power, so this whole thing was kind of the base. But now that they both just have base 5, now I can set the powers equal. But I had to get to that point where I had matching bases for that to work. So I get 2x plus x plus 2 is equal to 3. Okay, so now I want to combine like terms. 2x plus x is 3x. Plus 2 equals 3. I'm going to go ahead and try and get this x by itself. So first let's subtract the 2 across. Get rid of this plus 2. 3x equals 1. Now divide both sides by 3. And we get x equals 1/3. So that's our answer. Our answer is 1/3 for this one. And you could go back and double check that. If you plug 1/3 in here for all these, for these x's, it would work, but it's kind of a messy check. So the nice thing is you don't have to check it. 1/3 should work. There's no, force check on these problems. You just got to make sure you get those matching bases, and that's the big thing. Replacing the bigger numbers with, the smaller number 5 to a power. 125 becomes 5 to the third, that kind of thing. Okay, that's the first method. Honestly, I don't think this gets really used a lot in real life. It's kind of a slick trick method that we can use in homework problems where they give you nice ones. And I usually try to be nice and stuff. And so you might see some quiz or test questions where I give you this option because it's pretty straightforward. This one, not so much, but problems like this are really straightforward. But there are lots of problems where x is in the power where this method doesn't work, where you cannot get the bases to match. This would be an example of one, right? We have 3 to the x and we have 5. So here, I'm not going to be able to write it 5 as 3 to a power because the power that you put on a 5 to get 3 is not nice. It's like some weird fraction or decimal or something. So we're not going to try and do that. Instead, we're going to do a different approach. And so this is just talking about that up here. I stole this from one of the textbooks. It says to do these, we have an equation with x in the power, and you can't just get the bases to match. What you always want to isolate the exponential expression. So you always want to make sure this thing is by itself. No other stuff on that side, which we'll see more later and probably in the next set of notes. And then you either take the common log of both sides or the natural log of both sides. The only time we're really going to use the common log is for base 10. If it's not base 10, we'll pretty much always natural log for everything else. So if it's not base 10, use natural log. Now, why do we like natural log? Well, first off, we use natural log anytime it's not base e or base 10, because if you have natural log of something with a power, you can use the power rule and take the x power and pull it out front. Now, you could do this for common log as well, and so it really doesn't matter which log you do. You can do common log or natural log. I think most people just tend to do common log because it's a little bit less to write, which sounds silly, right? ln versus log, it doesn't really matter. No, it doesn't. But I know calculators all have the ln button on them, and it's just a little bit less writing, so I think that's typically what we do. So most of the time we'll use the natural log part, this natural log option, and we'll use the power rule. The power rule for logs. Remember that power rule that just takes the power and pull it outside. That's how we end up with this x outside. That's usually what we do. Now, the one exception, the only time we do something different, is if we have natural log of e, or if we do log of 10. So if we have a base e or a base 10, we're going to use natural log or common log in those situations. because natural log and e are opposites, they cancel. Log and base 10 are opposites, they cancel. You remember common log is base 10. And it's because of the whole inverses thing, that 10 to the x and log of x are inverses, and e to the x and natural log of x are inverses. So remember, inverses cancel. They cancel each other because they're opposites. And so that's why we use these. If you have base e, you use natural log because it's going to cancel the e. If you have base 10, use common log. And that's really the only time you use common log, just because base 10 is the only time where you can't really use natural log to cancel. You could still solve it with natural log and it would still work. You just have to do the other rule. We'll kind of, we'll use natural log when we have e, and we'll use common log when we have 10. And we'll show you that here throughout these set of notes. This is probably the most common way people use logs. If you're going to go on and take other classes in science or business, and you're going to end up using natural logs at some point, it's probably because you're going to be solving an equation where x is in the power, and you're going to need to solve for x. So if you're like dealing in business, we'll have equations where time will be in the power, to figure out how long it's going to take. So you'll solve for time t, and you'll use this idea. If you're in science or chemical reactions and chemistry, that kind of stuff, that'll also have equations with x in the power, the variable will be in the power, and you'll be solving, and you'll use natural log. And so that's probably the most common way you'll see this in future classes when you go to take other classes. So let's use that here, and we'll say it a lot because we're going to do that the rest of this set of notes, and then we'll actually do this a lot in the next set of notes. I shouldn't say the rest of the set, we have some other equations to do, but the next set of notes we'll do some practical real-life applications, and you'll see that this natural log on both sides will be like the most common tool we use for solving real-life applications. Okay, so let's try this. We want to solve this because x is in the power. We're going to take the natural log of 3 dx, and we're going to take the natural log of 5. So we always take the natural log of both sides, unless it's base 10. You're allowed to do this. It's just like square rooting both sides or squaring both sides. It's definitely allowed, so you can always do that to solve these. And then once you've done that, as soon as you have a natural log in there, you can use the power rule. This one, because we don't have e, we can't cancel, so instead we're going to use the power rule. We're going to pull the x out front. So we get x times natural log of 3 times natural log of 5. I don't really need the parentheses anymore. I could drop them. As soon as there's just one number, a lot of times we won't write the parentheses. I'm just being extra. I'm just putting lots of parentheses in for some reason. Okay, now I want to get x by itself. This is multiplication, right? When we put the x in front, it's multiplied. So the last thing we're going to do is we're just going to divide both sides by natural log of 3. Natural log of 3 is a number. It's some big long decimal. It's like if you took the square root of 3, you get some big long decimal. It's not a nice number, so we'll just leave it like this. We'll leave it in this form. I always get people trying to divide both sides by just a natural log. That's like trying to divide by a square root symbol without a number inside. It doesn't really work. You have to divide by a whole thing. So the natural log is attached to this 3. So I'm going to divide by the whole thing. So when I want to cancel this natural log of 3, I have to use an entire natural log of 3. Because it's, natural log is just something that does something to a number. So make sure you're understanding that, natural log applies to this number 3. So if you take natural log of 3, you get some decimal. So this is some decimal divided by the same decimal. They match, they cancel. And then over here, I have natural log of 5 divided by natural log of 3. That's not going to match. And so for this, to get an answer, we're going to actually type that in the calculator. And we're going to get some kind of decimal answer. It's not going to be a nice, pretty number. It's going to be some long decimal. So we'll do natural log of 5. Make sure you close that parentheses when you type in natural log of 5. Otherwise, it doesn't really come out nicely. If you end up with your second natural log actually inside or division inside. So we do natural log of 5, close it, divided by natural log of 3. Close it, and that's how we want it to look. And that gives us 1.465, I guess. And you'll go to whatever decimal places my lab would tell you to go to on the test. It should have some kind of instructions about going 2 or 3 decimal places. So that's what you do. If you wanted an exact answer, well, the exact answer would just be natural log of 5 divided by natural log of 3. But I believe your homework is really just going to have you do decimal answers. You're not going to worry so much about the exact answers like this. This is exact. This is decimal, so we didn't have to round it. That's why it's not exact, but that's close enough for us because we're just trying to get about what the answer is. Okay, that's the idea. You take the natural log of both sides, use the power rule to get the x out of the power, That's the whole point of these natural logs. We're trying to get at the x that's in the power. So it's not in the power anymore. And since the power rule always lets us pull us out, this works really well. But you have to have a natural log before you can do the power rule. I always get people on the test, they're trying to like take the x and pull it out right at the beginning. You can't just pull the x out. You need a natural log there so you can use that power rule for logs. That's the reason we can pull that out, using the power rule for logs. Okay, let's try another one. So again, got an expression with an x power, trying to solve for x. So we're just going to take the natural log of both sides. Take the natural log of 5.2 to the x. Take the natural log of 31. Again, power rule lets us take that power and pull it out. As soon as we have a natural log, that's what lets us do that. You can do it with any log, but we're just using natural log because it's a lot less to write. 5.2 equals natural log of 31. So we got the x out of the power, so now I can get this x by itself. We can undo multiplication, divide by the entire natural log of 5.2. I can do that to both sides. So it cancels this whole thing, and so we get x by itself, and it's equal to this, whatever natural log of 31 over 5.2 is. So I'm going to type in natural log 31, close it off, divide that by natural log of 5.2. And it gets this answer. So it's 2.083. 2.083. So that's the decimal, approximation. It's not exact, but it's good enough for us. So that's the idea. So take natural log both sides, use the power rule. That's how they work most of the time, because most bases are not 10 or e. So primarily, these are the most common things you'll see. There are some where the base is e or 10. So we'll solve a couple of those. And with those, you just got to remember that if it's e base, you still take the natural log of both sides. But instead of using the power rule, we're going to use the fact that they're inverses. Natural log and e are inverses. So we're still going to take the natural log of both sides. So we're going to take natural log of e to the x plus 2 and natural log of 15. But now, we'll use the fact that natural log of x and e to the x are opposites, or inverses. So inverses, e to the x and natural log of x, cancel. Inverses cancel. So that natural log and that e, they just cancel, and we're just left with the x plus 2, the power. So that's the reason. If you ever have an e base, you always want to take natural log of both sides, because then you can cancel that e base. The natural log cancels with e. So here we get natural log of 15. So now I just got to solve for x. I'm going to subtract 2 across and get rid of this plus 2 here. And get x equals natural log of 15 minus 2. Again, that's the exact answer. If I want an approximate answer, if I want a decimal, I'm going to just type it in the calculator. So I'm going to type in here natural log of 15. Make sure you close the parentheses because we don't want the minus 2 inside the parentheses, right? The natural log is only on the 15, not on the 2. So I'm going to close the parentheses, hit minus 2, and that's what I get. So I get 0.708. So 0.7708. That's a 7. Okay, 0.708. That would be our answer for that. If you have an e, take natural log. You'll see a few e's in the next section we do in outcome 5 or outcome 6, because a lot of real life applications will actually involve an e. Okay, let's do one more. This one is base 10, so the big difference here, and this is the only one we'll do it. We'll take common log. So we'll take log both sides. You could do it with natural log, but if you do it with natural log, you have to use the power rule. It's a lot easier just to take common log on both sides. Because if I take log of 10 to the 2x, this only works for base 10, because common log, this is base 10 log. Then you can just do log of 7 to the x. Here, base 10 log and base 10 here, they just cancel. So we get 2x. Over here, log of 7 to the x. This one, we do have an x in the power, so we do need to pull this power out. So we're actually going to be using the power rule as well in this one. This one's kind of silly or tricky because it's got x's in both sides. So this one, we're going to actually use the power rule and pull this out. So I wanted to show you this one because they put this in the homework, so I wanted to get you ready for it. if you have an x on both sides, what do you do? This one, we want to solve for x. So next thing we're going to do, we're actually going to get everything on the same side. So we can get all the x's on the same side. So I'm going to subtract this x log 7 from both sides. Because I'm trying to get rid of all, and get the x's all on the same side. So I get 2x minus x log base of 7 equals 0, because I took away everything on that side. And now when you get all the x's on the same side, what you can do is you can factor them out. So I'm going to pull all the x's out as a greatest common factor, leave behind a 2 minus log 7. So anything that's not an x got left behind. And then I just have to divide that across. Well, the trick here is when you divide anything into 0, you still get 0, right? 0 divided by anything is still 0. So when I divide across, I'm just going to get 0. So kind of a weird one in the homework, and that's really why I wanted to show you this part. Like I said, if you're doing a quiz or test question, you might see one where they have you dealing with a log base 10. They're not as frequent, where you might not have to do all this work. You might have one where you just get to cancel the logs. But mostly we'll use the natural log. Natural log is definitely more common. Over here we get 0, so it just ends up being that x is equal to 0 on this one. That's the natural log. Which makes sense, because if you make both powers 0, then you'd have 10 to the 0 and 7 to the 0, and they both become 1. That's actually the only way this one works, is if they both become 1s, because you can't really make 10 equal 7, but you could make this be 1 and that be 1, and then you get the same number. So that's it. Okay, that's the first half of this section. There's actually more, because so far we've just been solving equations where x is in the power. That's the big thing here. X is in the power. The big thing I want you to take from this is that 9 times out of 10, if x is in the power, you're going to take the natural log of both sides. We'll see that next week or next section notes. That's going to be basically our go-to. If we see an x in the power, we'll take the natural log of both sides. And that is the method. The rest of this set of notes is about what happens if x is inside a log. What if you're trying to solve for x that's inside the log? Well, there's also two approaches for this. And the first approach deals with equations where you only have one log and you have something else. And the trick here is just to rewrite it in exponential form. So to do this, we're going to get it to look like this form. This is our log form, where we have log of a number equals number. That's what this looks like, right? Log of a number, x minus 5 is just some number, equals a number. And then we're going to rewrite the equation in exponential form. So we're going to write it like this, where we have a base and a power and a result. And then you can solve it. That's the big trick here. It's way easier to solve log equations if you don't actually have a log anymore. So we're going to take this and we're going to rewrite. Remember that the base of your log is the base of your exponential equation. So I'm going to have 4 to some power. Remember the answer to your log is always the power. So my power is 3. And 4 to the third is going to give me some result. Well, the result I'm looking for is actually x minus 5. So I get x minus 5 as the result. So remember, base of the log is the base. The log gives you a power, and the stuff inside the log is what that base and that power give you. That's how we rewrote it this way. Once you have it like this, now you're just solving for x. Not a big deal. First, just do 4 to the third. 4 times 4 is 16, times 4 is 64. So it's going to be 64 with x minus 5. And add 5 to both sides. Get rid of that minus 5 on this side. So I get 69 equals x. And I'm done. That's our answer. That's it. So if you can rewrite it in exponential form, they're usually pretty easy to solve. That's the idea, is get it this exponential form, because then you just have to get x by itself and get an answer. So let's try another one like this. Again, if it's like this, where it's in log form, log of a number equals a number, then you can rewrite it. Base is always the base of your log, so base is 2. The answer to the log is your power, so the power is 5. The result of 2 to the 5th is 4x plus 8. That's our result. And then we're back to solving for x again. So we rewrite in exponential form. That's the big trick on both of these. Rewrite in exponential form. Okay, so here I'm going to solve this. So I'm going to go ahead and do 2 to the 5th first. So 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So 5 2's makes 32. So this is 32 equals 4x plus 8. Let's subtract 8 from both sides. So subtract 8. Get rid of this. So I get 24 plus 4x. I'm going to divide both sides by 4. And we get x equals, what is that, 6? Yeah, this is 6 equals x. So our answer for this one is 6. Now I do have to warn you about something that's going to show up later. It doesn't actually affect these two problems, but it's something important. As this method of solving logs can actually give you extraneous solutions. It is possible the answer you get doesn't actually work. Now why does that happen? Well, remember logs only work on positive numbers, and when you do this, when you solve logs like this, it is possible to get an answer that if you put it in the log, makes the stuff inside the log negative. So one of the things you should always check is you're solving an equation where x was inside the log, you should always check that the stuff inside the log is going to be positive, bigger than 0, when you plug the number in. So if I see x is 6, I'm going to plug that in here and I get 4 times 6 plus 8. I want to make sure that is positive. Well, positive times positive plus positive is positive, so it is greater than 0. So we are okay for this one. So yes, this one checks out. Like I said, it doesn't really affect these problems. Same thing up here. I check the 69 and plug it in here to check to see that x minus 5 is greater than 0. That would be my check on this one. I'm just looking for the stuff inside to be positive. If we put a 69 there, 69 minus 5 is, 64, and that's fine. It's greater than 0, so it checks out. So that's something we're always going to look for when we're solving these log equations. If you're solving and x was inside the log, you have to go back and make sure that when you're done, if you put that number in, the stuff inside the log is positive. And it will show up later in these notes. You'll see one where it doesn't work, and so we're going to have to take that out. Okay, next one. So this one, same idea. We want to rewrite this, but before we can, we notice that there are actually 2 logs, not just one like the last ones. The trick here is the condensing thing we've done before. So last set of notes we learned about, or maybe it was 2 sets ago, I forget which. We learned to condense. We learned that we could take 2 logs and we could combine them, as long as they have the same base, which these will. You could combine them using the product quotient or power rules. These ones are a plus, so we can use the product rule. So we'll use the product rule that says that if you have the addition between 2 logs, you can condense it back down into multiplication. So I get log base 6 of first x plus 3 times x plus 4. That whole thing's inside this log, so I'll put a big bracket around there, equals 1. So I don't care what's inside the log. As long as I get down to a single log equals a number, then I can rewrite. So that's the trick here. We're going to condense it down first, and then we'll rewrite. So the base is going to be 6. That's our base. The power is 1, because the answer to our log is 1. And the result we get is x plus 3, x plus 4. That's our result. Okay, 6 to the first is just 6. We're going to leave that alone. Over here, this is factored, but it doesn't work to have it factored if it's equal to a number other than 0. So this right here, we actually will have to multiply out. So we're going to FOIL that. Remember, FOIL, you do the first. X times x is x squared. Outer, x times 4 is 4x. Inner, 3 times x is 3x. So I take 4x plus 3x, I get 7x. I'm just combining them now instead of doing it later. 3 times 4 is 12. So if you don't believe me, you can sit there and multiply out. You get, x squared, 4x, 3x, and 12. And the 4x plus 3x gives me 7x. So I FOILed that out so that now I have my quadratic. I can get it equal to 0 if I subtract 6 from both sides. I subtract 6. So I want to get that equal to 0. That's the way we solve quadratics, is we always get it equal to 0. And then either use the formula or we factor them. So 0 equals x squared plus 7x plus 6. And this one actually factors, so we'll just go ahead and factor it. If it doesn't factor, remember you can use the quadratic formula, that x equals negative b plus y squared b squared minus 4ac. It's ridiculous, but yeah, that's the quadratic formula. If it doesn't factor, that's what you go with. But most of the time on problems like this one, I would give you one that factors. Okay, this factors into both x's. It needs to multiply for 6 and add for 7. So it looks like 6 and 1. They multiply for 6, they can add for 7 if they're both positive. So 6 and 1, multiply for 6, add for 7. Okay, now that we got it factored, I'm going to set both parts equal to 0. That's why we factor when it's equal to 0. So we get 0 equals x plus 6. 0 equals x plus 1. Subtract 6 across, so x equals negative 6. Subtract 1 across, so x equals negative 1. So those are our two answers, right? We got these two numbers for answers. But we talked about last one, we need to check. Now this time, there's actually two different logs, so we got to check both of them. We got to make sure that both of these statements are true. That x plus 3 is bigger than 0, and x plus 4 is greater than 0. So both of those have to be true. If either one of those fail, the number doesn't work. So if I try negative 6, well, negative 6 plus 3 bigger than 0? No, it's not, right? It's not bigger than 0, which means negative 6 doesn't work. That's not a valid solution. So we got it using this technique of rewriting, but it doesn't actually work when you go back and plug it in because you cannot take the log of a negative number. It never works. You can't ever do it. So that's something you have to really watch for if you're solving log equations like this. You always have to go back, plug the number in, see does it make the insides negative. If you try and put the log in there with negative 6 plus 3, which is negative 3. You put log 6 of negative 3. Your calculator will tell you it doesn't work. It doesn't exist because you can't do logs of negatives. If I try negative 1, this one's fine, right? Because negative 1 plus 3 is bigger than 0. That checks out, right? Negative 1 plus 3 is 2. Negative 1 plus 4 is bigger than 0. That checks out because that's 3. So this one actually works for either, so this one is good. No rule says I don't think that one of them has to work, one of them has to fail if there's two answers. So you always want to check both and just make sure they don't mess up. If they give you a negative, they don't work. Okay, so that's that. There's one more thing we have to deal with log equations, and that's when everything has logs. So we have an equation like this where it's all logs. There's not really a number by itself. And instead of using the rewrite trick here, we're actually going to use a different method. We're going to use the one-to-one property of logs. The one-to-one property basically says that if the logs of two numbers are equal, then the stuff inside, the things that inside the numbers, have to also be equal. So what we'll do with an expression like this with all these logs is we'll get it so there's a single logarithm with coefficient 1, you can get all the powers in, on each side, and then you can just take those two logs and set the insides equal, and then solve after that. So let's see the idea here. So first off, the first thing we're going to do here is we're going to use the power rule to condense. Because first thing we want to do is condense this, and to condense, the first step would be taking the multiplication in front and putting it inside as powers. So that's going to be the first step. So it's going to turn into log of x plus 4, the quantity, squared, still minus log of 3, equals log of 12. So that's the first step. Now that's just dealing with the fact that here we have a power, because remember when you have multiplication you can turn it back into a power. So that was the power rule first. Now this minus, I'm going to use the quotient rule. Remember the quotient rule takes the subtraction between two logs and turns it back into division. So that'd be my next rule. So I'm going to take this and turn it into a log of the first thing, which is the x plus 4 squared, over the second thing, which is a 3. And that's what we have log of. Just take those two logs and combine them into a single log. Equals log of 12. Okay, this is the idea. Once you get a single logarithm equals a single logarithm, once you just have one log on both sides, then you can just drop the logs. If two things with logs are equal, then the stuff inside has to match. I can't take log of 12 and log of 7 and get the same answer. They both have to be log of 12. So all this stuff in here has to equal 12. That's what this is saying. That the only way these two are equal is stuff inside is equal. So I'm going to set the insides, so without the logs, the insides equal. So I'm just going to solve this. This one, first off, I'm just going to get rid of this fraction. So I'm going to multiply both sides by 3. Now I can get rid of this fraction here. So I get x plus 4 squared equals 36. Next thing, because this is already factored as a squared thing, I don't have to FOIL this one. I can actually just square root both sides and use the square root property. Just don't forget, if you use the square root property, you use the plus or minus on the number side, not the letter side. So square and the square cancel, so we just get x plus 4 on this side. Square root of 36 is 6, so I just get plus or minus 6 on this side. Last step, I'm going to subtract 4 across. I like to put it in the front, but it doesn't really matter. I'm just putting it in the front there so I can have the plus or minus in the middle. That's always where I like to have it, plus or minus in the middle. This one, I'm not done here because I can finish solving it because I can do -4 plus 6 and get 2, and I can do -4 minus 6 and get -10. Those would be my 2 answers for this one because -4 plus 6 is 2 and -4 minus 6 is -10. Now I'm not done yet because just like the last section, we are solving with x's inside of logs, so we have to check. We gotta go back and check. We actually only have to check this one here because this is the only one with an x. So we have to check that x plus 4, that quantity, is positive. So when x plus 4, that quantity is bigger than 0, will be positive. So what about 2? Well, if I put 2 in there, I have 2 plus 4, which is 6, and that is bigger than 0. So that checks out. So 2 is a valid answer. We could definitely keep 2. What about 10? -10. Well, if I put -10 plus 4, bigger than 0? Nope, it's not, because -10 plus 4 is -6. So that one fails. Now, it's not a rule that only negative numbers fail. You can definitely write equations where the positive fails and not the negative. I just have a couple of examples where the negative fails. So that's not a rule. You can't just assume. Be careful about that. I always get people that just assume, oh, that's a rule, right? No. But you just need to check. Just plug it back in there and see if it's going to make it negative or not. If I put that number in there, it's going to mess it up. Do one more of these, and then that's it for this section. So again, the idea here is we're going to condense. Always condense first until we get a single logarithm on each side. And then once we have a single logarithm on each side, then we can drop the logs. This one, because it has a minus here, we're going to use the quotient rule. The quotient rule tells you that you can take the minus between two logs and turn it into a division. So this becomes log base 5 of x plus 12 goes on top over x plus 5 goes on bottom. Equals log base 5 of x. So again, we dropped, the minus quotient turns back into a division. Now that we have a single log on both sides, now we can drop the logs. So we can drop those logs and just set the insides equal. So again, x plus 12 over x plus 5 equals x. Okay, now I got to solve this expression. To do this, I'm going to just go ahead and multiply by x plus 5 on both sides, because that will get rid of the fraction. So I'm going to multiply by the LCD, which in this case, the LCD was x plus 5. So I get rid of the fraction on the bottom on this side, because you multiply by the top, by the bottom, they cancel. So you just get x plus 12. This I can distribute. X times x is x squared. X times 5 is 5x. Now I've got a quadratic, right? I got an x squared. So I'm going to get this equal to 0. So I'm going to subtract x across. I'm going to subtract 12 across. This guy and this guy. So we get 0 equals x squared plus 4x minus 12. Okay, now that we have it as a quadratic, we want to solve this, so we're going to factor it if we can. I think this one does factor, right? So 2 times 6 is 12. If I make one of those positive, I can get a positive 4. So let's do that. We'll do x and 2 and x and 6. And I think I need a positive 6 and a negative 2. That way they add for 4, but they multiply for negative 12. So I get x minus 2 equals 0. X plus 6 equals 0. Say both parts equal to 0, because if your product is equal to 0, then each part could be equal to 0. Add 2 across, you get x equals 2. Subtract 6 across, you get x equals negative 6. So that's the idea. If you can get a single logarithm on both sides, drop the logs, and then solve what's left. And this is an equation we solved before. So that's why I'm not worried too much about it. Just expression with having a fraction. So we just got rid of fractions. After you're done, though, you do have to check, right? The check always has to happen. So anything with an x in it, any log with an x in it needs to be checked. So we need to make sure that x plus 12 is bigger than 0, the x plus 5 is bigger than 0, and x is bigger than 0. We need all those things to be true. So first, if I put 2 in here, I'll check out, right? 2 plus 12, that's 14. That's bigger than 0, checks out. 2 plus 5, that's 7. It's bigger than 0, so it checks out. 2 is bigger than 0. That checks out. So this one too, that's a valid answer. It's great. Now we got to check both. Let's check negative 6. So negative 6 plus 12, that's bigger than 0. It checks out, so far so good. Negative 6 plus 5, though, is not bigger than 0, right? That one fails. So this negative 6 fails. As soon as it fails one of the checks, we toss it. And negative 6, plus 5 is negative 1. It doesn't work. Also, negative 6 by itself, when we do the last one, is not bigger than 0. So it failed there as well. So really, we knew as soon as we saw the x by itself that any negative number was going to fail in that case, because they would already just be negative when you put them in. Okay, so that's it for outcome 5. So outcome 5 is all about solving these exponential expressions where x is in the power. The most common way we do that is taking natural log both sides, and then solving these log equations, where you either get the two logs equal and then drop the logs, or we use the rewrite, where we have just a single logarithm, and we just rewrote it in exponential form and then solved it. So that's going to be that. We will come back to some of these techniques on the next set of notes, because the next set of notes is really just applications of these, of solving exponential and log equations in the real world problems versions of those. So that's it for today. I'll see you on the next set.